Yes.
So the talk will be about indexing, image searching, and sublinear time. It's a joint work with Ian and Gonzalo. So I'll start by defining the problem that everybody already knows. So this is we're given a string t of length n over an alphabet of size sigma, and we store it in a data structure. And for any query string q, we would like to report or count all occurrences of the string p in the text t. And there are generally, this data structure is called string index, and there are three main criteria of efficiency. It's query time for both counting and reporting queries. It's space usage, and construction time. So in this talk, I will concentrate on the third criteria, and I will describe a data structure with efficient construction time. So there are several different trade-offs between construction time and query time described in the paper. In this talk, I will discuss just one trade-off. This is a data structure that uses optimal space, asymptotically optimal space, and log sigma bits, where sigma is once again the alphabet size. The counting queries are answered in this time, so the time is proportional to the length of the query string in words, or q divided by log base sigma n, and there's also an additive factor, log n times log sigma n. And if we want to report the locations of every occurrence, then we'll need to spend roughly log n time for each occurrence. And the construction time is the same as in the data structure of Kemp and Kachumeka that was just introduced in the previous talk. And this is n log sigma divided by the square root of log n. So now to this, why doesn't it scroll? Okay. To compare with previous results, here on this slide, you can see main results obtained by in previous works. And you can see that there are many data structures that can be constructed in linear time, linear in the size of the input string. And the query time is essentially either proportional to the length of the pattern, in many cases, plus some additive factor, additive term, or it's just, for example, in the work of Belazug and Navarro, the time is just proportional to the length, the query time is proportional to the length of the query pattern. And in some cases, we can achieve even the optimal query time in words. For example, in the data structure of Monroe and al. And others from 2019, the query time would be proportional to q divided by log base sigma n plus log to the, essentially log to the epsilon n. There is just one paper that achieves sublinear time when the input text is sublinear construction time, and this is in the case when the input text is in the packed form. And this is, as I said, it was just introduced in the previous talk. The construction time would be n log sigma divided by square root of log n. So if we use the BWT construction algorithm of Kemp and Kachumeka, then combine it with rank and select queries using covalent trees, then the query time for counting queries would be proportional to the length of the pattern times 1 plus log base omega of sigma. Omega is the word size. So in this talk, I will introduce a data structure that has the same construction time as the best BWT construction algorithm, And at the same time, the time to answer queries is proportional to the length of the pattern in words. So we assume that the query pattern is also given in packed form, and then we achieve the query time, which is optimal in the length of the pattern, but has some small additive term. Oh, this is for the counting queries. Okay, so now how do we achieve it? We combine several different methods. First is the reduction of indexing problem to range searching. It was, I think, first introduced in the paper on geometric BWT in 2015. Then there is we also use a data structure for LCE queries. We will use the optimal result from stock 2018. And we also use a number of different techniques such as subsampling and pre-computed solutions in the case when patterns are short. So we will combine all three techniques. And okay, I will give a general description, but will not go into much details. And I will just concentrate on counting queries. So the idea of reduction of the problem to range searching is as follows. We divide the text into blocks of equal size delta for some parameter delta. And every block is viewed as one meta symbol over an alphabet of size sigma to the power of delta. And once we divided this text into blocks, let's call this text T prime, we construct an index data structure, for example, a suffix array for T prime. So to support pattern matching queries on the initial text T, we essentially need two components. We need the suffix array on T prime, or an indexing data structure on T prime, and we need a range searching data structure on pairs on two-dimensional points that correspond to suffixes of T prime. So for example, if we look at the occurrences of some pattern P, then all occurrences can be classified according to the first position where they cross the meta symbol boundary. So here on this slide, you can see the case when the query pattern is aligned with the meta symbol boundary. It's also possible that the query pattern starts one position to the left of some meta symbol boundary, or two positions to the left, or three positions to the left. And okay, in this example, delta equals to 4. So there are just 4 different cases. So for any fixed value of this shift, let's call this shift J, all occurrences essentially correspond to occurrences of the pattern Pj plus 1, Pj plus 2, Pm minus 1, preceded by the first J symbols. So essentially in reverse order. So we must identify all occurrences of the pattern P without the first J symbols and preceded by the J symbols in the reverse order. And we have to do it for all J between 0 and delta minus 1. So we need then to construct a set of two-dimensional points. Every two-dimensional point is a pair that corresponds to an index. So for example, if you consider this blue index that starts at position K, then the pair will correspond to the index or position of this suffix, of this blue suffix in the suffix array SA prime. And the second component will correspond to this green meta symbol and in reverse order. So the symbols of the green meta symbol listed in reverse order. And then, while essentially we need to report all occurrences of some pattern preceded by some several symbols. Of course, all suffixes starting with some pattern correspond to an interval, let's say I1, I2 in the suffix array, and all meta symbols are integers between 1 and n, and therefore reverse meta symbols starting with a certain string, let's say pj minus 1, p0, also correspond to some interval j1, j2. So now, how can we report all j occurrences for some fixed j? We would find the suffix range I1, I2 of the pattern with first j symbols removed, and then we'll answer range searching query. We'll report all pairs, index and reverse meta symbol, reverse preceding meta symbol, which lie in this range I1, I2 times j1, j2. So each query can be answered in log n time roughly. Therefore, if we sum over all j, then the query time will be delta times q divided by log sigma n plus delta times log n. So the problem is this first component, because the query time is not proportional to pattern length. It's proportional to pattern length times delta. If we make delta, for example, something like log n, then the query time or the counting time is not good at all. So to get rid of this, we'll essentially use an LCE data structure. So now the task is, suppose we, for example, know the suffix range of the pattern P and want to find the suffix range of the pattern P1, which is P without the first symbol. Now in this case, so here in this example, the blue range in SA prime is the range of the pattern P. In the suffix array of T prime, we select an arbitrary suffix from this blue range and find its position in text T prime. Now, if we shift one position to the right, to this dark green area in the text, then this will be, the dark green area will be the starting position of some suffix in the text, such that the first q minus 1 symbols of this will be the pattern P without the first symbol. Now, so this will be some occurrence of pattern P1 that starts in this dark green area. Therefore, now what we need to do, we'll need to identify the range in SA prime such that the range of suffixes that start with the same pattern P1, or this will be the range of the largest range of suffixes such that LCP of the suffix and the dark green suffix is at least q minus 1. So we'll find the smallest such suffix and the largest such suffix. So once again, if we look at this suffix starting position k delta plus 1, the LCP of this suffix. So we're looking for the range of suffixes with LCP at least q minus 1. So this can be done. We can find this area in the suffix array, the range of P1, by just doing binary search. And of course, we can compute the longest common prefix of any of the suffix starting at the leftmost dark green point, and the suffix and any suffix in SA prime using the LCE data structure. Now the query time is definitely better. It just becomes proportional to the length of the pattern in words plus log n times delta. Now, in fact, we can even further reduce the query time. To do this, we observe that this query time is already optimal when the length of the pattern is large. So if q is larger than, let's say, log squared n, then this first term will be consumed by the second term, and it will be just optimal q divided by log base sigma n. Now, to deal with short patterns, I will just very briefly explain the idea what we will do. We'll again look at the area SA prime and select some suffixes in this area. So the suffixes are shown with these red squares. Let's say we select one suffix out of log to the power of 10n. And then we'll look at all possible prefixes of these suffixes of lengths up to log squared n. So we'll have about n divided by delta divided by log to the power of 10th n and multiplied by log to the power of 4th n. So we have some small number of suffixes or some small number of strings. And then we pre-compute this suffix jumps for all strings in this set. So when we have done this, this can be done because the number of the strings is relatively small. The problem of searching for suffix jumps is reduced to the same problem on a smaller set. So what we will do, we'll first identify the range of the new pattern P1Q in among the selected suffixes. Let's say this is these two red suffixes. And then all we need to do is just look in this green area or look in two green areas. And those are just areas between two selected suffixes. So the length of this area or the length of this interval in the suffix area, SA prime, is polylogarithmic. And again, if we do binary search, the time to finish this search and to find the exact suffix range of P1Q will be log n. So in all this description, I didn't consider one special case, and this is the case when the query pattern is very small. So when the length of the pattern in symbols is smaller than delta, then it can happen that the occurrence of this pattern is entirely within one block or within one meta symbol of T prime. So we cannot apply this approach with range searching and with LCE queries and so on in this case, but fortunately we'll make delta small, and therefore this special case can be dealt with using lookup tables. Again, lookup tables can be constructed quickly. Now, so to get the result that I announced and the first slide of this, we'll need to set delta to be log base sigma of n. So the query time will then become q divided by log base sigma n, or the length of the pattern in words, and plus log n base times log sigma n. The construction time is n log sigma divided by square root of log n. Essentially, the bottleneck is the same as in the previous talk. It's n log sigma. This is the time to construct range searching data structure, or it will be some wavelet tree or some variant. Let's say it's actually a variant of a wavelet tree that we're using. It's a wavelet tree with some additional data structures on top of it. And the space usage is n log sigma bits. So there are many other technical details. For example, we need to describe in the paper how all these data structures are constructed. And there are also some details about work with short patterns and also about reporting that I didn't address in this talk. So at the end, let me ask one open question. We achieved a data structure with query time, which is probably optimal, or optimal unless we achieve some major breakthrough in counting conversions and similar problems. And the question, can we get rid of these additive factors in query time? Right now we have this, the query time is like this. There is this log n log base sigma n additive factor. it can probably be reduced, but can be achieved the optimal querying time, which is just proportional to the length of the pattern in words. That basically finishes my talk, so thanks for your attention.
Thank you for a nice talk, Jakob. Are there any questions?
Hi, Philip. I have one. I'm Solon.
Yes, hi, Solon. Go ahead.
Hi, Jakob. Thanks for the nice talk. So